Hello, my name is Jonathan Munro from the University of Bristol. I will be presenting our work on multimodal domain adaptation for fine-grained action recognition. Fine-grained actions are short, atomic actions that last a matter of seconds. For example, cut tomato is a fine-grained action, whereas prepare salad is coarse-grained. Due to the difficulty in collecting and annotating many examples of fine-grained actions, datasets are often curated from a single location with multiple individuals. Our previous work, Epic Kitchen, scaled to 32 native environments, capturing natural, unscripted actions. However, the number of environments is significantly less than coarse-grained action recognition datasets, such as kinetics. This leads to environmental bias. We utilize the multiple environments within Epic Kitchens to evaluate domain adaptation. We select 3 environments which we consider as separate domains, D1 to D3 on the figure on the right. This paper focuses on unsupervised domain adaptation where unlabeled data from the target environment is available. Note that collecting unlabeled data can be relatively cheap compared to the expense of collecting annotations. We train a 2-stream I3D architecture with late fusion of RGB and Optical Flow. Inclusion of explicit motion information has been shown to benefit action recognition. The model is trained on a single source environment and evaluated on a novel target environment. As both source and target data are from different participants in different environments, there is a domain shift. This is evident from observing the T/S&E plot of our source and target distributions, which have minimal overlap in RGB. A classifier trained on the source does not perform well on the target. Our first novelty is utilizing the multimodal nature of videos for domain adaptation. Different modalities will be robust to different domain changes. With inspiration from self-supervision in video, we learn the temporal correspondence of modalities. This can be utilized without the need for labels. We thus train our self-supervised classifier for both source and target domains. Corresponding inputs contain modalities that are sampled from the same action instance. Non-corresponding inputs are sampled from different action instances. We train a binary correspondence classifier that takes input concatenated RGB and flow features. The self-supervised classifier C learns to predict if modalities correspond. The correspondence objective is learned over both source and target domains jointly with the multimodal action classifier. By detecting if RGB and flow modalities correspond, common features to both domains are learned. Incorporating self-supervision separates the target samples and feature space into clusters that are potentially class relevant. The domains, though, remain distinct. To explicitly align the source and target domains, we utilize domain adversarial alignment. The domain discriminator predicts if a sample input belongs to the source or target domain. The gradient reversal layer negates the gradient and backpropagates this to the feature extractor. The feature extractor is thus trained to maximize the domain discriminator's loss. Both RGB and optical flow modalities are aligned with adversarial training. Our training jointly optimizes the losses, backpropagating through the features end-to-end. Features are optimized by the classification loss, the adversarial loss, one per modality, and the self-supervised alignment loss. Here we show an example of action cut from 2 different domains. The video on the left is from the source domain, and the video on the right is from the target domain. Without alignment, these actions are far in feature space. With self-supervision, these actions are brought closer together, but not fully aligned. With the addition of adversarial training, there is significant overlap between domains. Our results show that both self-supervision and adversarial training benefit the transferability to the target domain. However, training both objectives are shown to be complementary, leading to the largest improvements. Our method benefits the performance of both modalities. However, largest improvement is for RGB, which is considered to be less robust to environmental changes. Visit our poster for further discussions, and thank you for listening.